And we've got the very person to talk about that. We have Professor Scott from the Cognitive Neuroscience Faculty of the University College of London. Yeah? And her favourite research topic is laughter.
Now you get to spend 5 minutes watching me try and get on the stage. Can you do this? Oh, yes. Thank you. Brilliant. Now, Tiernan and Natanya are very kindly started. Fantastic. So if you fall asleep at any point, you can buy my book, okay? It's not about laughter, it's about brains. Manage your expectations for the next 20 minutes, I would say. So I'm going to tell you 10 things you need to know about brains. Spoiler alert, there are more than 10. But the first one is that you get one. When I look at this picture of me as a little girl here on the left, that's me around age 2.5, 3. And every single bit of that little girl isn't there anymore. And I don't mean metaphorically because now she's a woman. I mean literally, there's a cycle of death and rebirth in body parts throughout your whole life. You get about a whole new body roughly every 10 years, which is when you get a whole new skeleton. Much of the rest of it regenerates much more quickly, except for 4 parts of your body, okay? If you're female, the gametes, your ova, you are born with those. You have those all your life. The cells in the crystalline lens in your eye, you have those all your life. You're born with them. You have them your whole life. The cells in your ear, the hair cells that turn sound into electricity the brain can process, you have those your whole life. And your physical brain. The cells that make up your brain, you have them for your whole life. You don't get new bits of the brain as you get older. There is one critical potential change to this, addition to this I'll say right at the end. But I think that's worth bearing in mind. This is your brain. Anything you learn, anything that changes about you, anything you learn from today is because your brain itself has changed to reorganize to learn that knowledge. And as far as we can tell, there is no known limit to how much information the human brain can store. So this massive brain that you have, and you have about 86 billion brain cells, make this extraordinary network that can remodel and change itself continually to store information, to change, to reflect all the experiences you've had. Now, another thing you need to know about brains is that brain cells, neurons, are extremely strange cells. Cells vary widely throughout life. A cell in your liver is very different from a red blood cell. But brain cells, neurons, have this very strange characteristic. They've got a central cell body where the nucleus lives, and then they have these long projections going off. And you can see that those long projections are sort of dusted with these fine little buttons. And that's actually how the cell is able to send messages, because those little boutons, or synaptic boutons as they're known, they can make connections with other brain cells. So this is how the cells have their power. They're not just sitting there stacked up with other cells. These long projections let them talk to other brain cells, and critically, they can grow new projections and they can grow new buttons that enable them to talk to other brain cells. So this is part of the flexibility of these brain cells you're born with. They can change, they can grow. They also can send messages. Within the brain cell, within a neuron, messages are sent electrically, following something called biological electricity, which I'll come back to. So within that brain cell, a message is sent using an electrical discharge. Between brain cells, where those two little boutons make contacts, that information is transferred chemically. So neurotransmitters send that message. It's quite extraordinary when you think that the possibility of all the things that brain cells can do started with the very first appearance of unicellular life. Unicellular life is giving you a little organism that is just one cell in its size. So you may have drawn amoeba when you were doing your biology O-level. Something that's really critical to the formation of unicellular organisms, for cells to exist, is the cell membrane. Because life evolved in water, And water is quite a hostile place to be if you are a little bag of chemicals, like life is, because water will come into the cell and explode it, it'll wash things away. What the cell needs to do is to be able to keep water out, to control the movement of water. And the way that cells do this is by moving ions of potassium and sodium, sometimes calcium, across that membrane. So that membrane is dotted with these little gates that pump potassium and sodium around, and they maintain the integral sort of salinity, the chemical environment within the cell, so it doesn't just burst. Now that is how neurons generate electrical charges. Instead of making current electricity or static electricity, what they do is they pump potassium and sodium ions in different directions across the cell membrane. Because they have a different ionic charge, you end up with an electric potential across the cell membrane, and when that discharges, it really rapidly causes a rapid generation of something called an action potential, which shoots along the cell membrane of the nerve cell and sends that electrical signal. Now, something else that I mentioned was the chemical nature of this information, and that's also exploited in unicellular organisms. So this little chap here is quite an interesting little unicellular organism. What he's able to do is he's got a little flagellum at the top there, and when he spins that around, he can move. Now, the interesting thing about these chronoflagellates is under certain circumstances, they get together with a lot of other chronoflagellates, and they start to move around. So you can see here, there's lots and lots of these little chaps, or chapesses, all gathered together, and they can actually move in quite a coordinated way. And they're doing that by coordinating how they move those little flagella, those little tails, and they're doing that by releasing chemicals that mean they all move in synchrony. So that's the basis for transmission of information chemically across cells. That's the first basis for how our brain cells are able to transmit information. Extraordinarily, in evolution, we haven't developed anything new to control this. So everything that in your brains is controlling how your brain generates an electrical discharge, or how it is controlling the release of generating and releasing neurochemicals to communicate with other brain cells, it's already all coded for in these really early forms of life. It's absolutely dizzying to think about. All that's happened in evolution is that it's all the building blocks for brains were there right at the outset. Now, as soon as you are a more complex kind of multicellular organism who wants to move around the world, you absolutely need to have brain cells, nerve cells that can communicate around the body so that you can tell where you're going. You can pick up whether there is light or dark, what is up, what is down, the sorts of things whatever your organisms needs to know. And as far as we can see, this evolved once. Comb jellies evolved slightly earlier than jellyfish, and they had a different sort of nerve cell. Happy to take questions on that. Very recent data has come through. And then shortly afterwards, jellyfish appear, and they have what are called nerve nets, and their nerve nets are made up of brain cells, nerve cells that look very similar to what we'd find in your brain. And this enables them to do a lot. They can detect light and dark, they can detect gravity, some of them are able to hunt pretty well, they can detect touch if they're anywhere near their prey. So those nerve nets are doing a lot, but they still don't have something you would consider to be a brain. What you find is that brains appear shortly afterwards in the evolutionary tree, associated basically with more complex bodies. So this is Piakia gracilens, this is the fossil of this rather unprepossessing worm-like creature, which is the first animal we can find in the it was appeared in the Precambrian period in the Burgess. It's one of those Burgess shale animals, I think. It's the first animal that seems to have a very distinct brain. So it doesn't have just nerves throughout its body which are joined up. And this seems to be associated with the fact that it had a more complex way of moving. So it was swimming through the water like this. It's got a segmented body. It has a distinct head. And that's where brains go. So this is where we're first seeing brains evolving alongside bodies. If we go back to your brain and my brain, one of the things that's quite extraordinary about them is, bearing in mind you are born with the brain you're going to have for your whole life, of course it's not the same. Your brains change incredibly rapidly through the first few years of life, I think your brain gets 4 times larger between birth and the ages of 6. So it's growing really rapidly. So that's individual brain cells getting bigger. That's not you growing new parts of your brain. And then, of course, it's also being massively influenced by the sorts of experiences that you have, because anything you learn, anything you can do, anything you remember is happening because your brain has changed to encode that information. If we think about the growth of the brain, this is just going through teenage years. Teenage years are extremely important for brain development. And what you actually see as adolescents go from sort of puberty through to the early 20s, as the brains are getting bluer there, they are showing more and more adult-like patterns of connectivity. So it's very interesting, both that there's a huge amount of growth still going on throughout the teenage years, but also the brain areas that are showing the adult-like profile last of all, tend to be towards the front of the brain areas associated with sort of decision-making and planning, and lots of love to any teenagers in the room. They're not necessarily a group of people known for brilliant decision-making or unrisky decision-making, and it's because of their brains. Their brains are still growing. Teenagers are brilliant. We should give them lots more responsibility and enjoyable things to do in life, but their brains are not yet adult brains, and they think differently to adults. Often that's an advantage. So by the time you have an adult brain, you've got something that's reflecting both the fact that you've been through this brain maturational process, but also everything about both the brain you were born with and the chances and the opportunities that you've had to change that brain. If you really want to change your brain, learn a musical instrument, learn to read, learn to speak multiple languages. All of these things will be reflected in your brain structure and your brain function. Because some things are very different across cultures. So this was a study my PhD student did in Namibia, where she was working with the Himba people, and she was interested in the recognition of emotion from the voice. And what you could see there was a guy, any guesses what emotion he was expressing at the start there? Happiness. It's a very positive emotion, wasn't it? Anything else? Was it high in energy? Was it low in energy? High in energy. It's actually triumph. Now that's an example of an emotion that is culturally specific in its expression, because we don't hear that as sounding triumphant. And if you play him a recording of someone back in London going, woohoo, or something like that, he doesn't hear that as sounding triumphant. Those are recognizable emotional states. He knows what it means to celebrate something, but the expression of it is culturally determined. That is not something that is universal to all humans. Anybody notice what happened at the end? He started laughing, and it's exactly the same. So lots of aspects of our emotional expressions are also completely universal. As far as we can see, laughter is a highly universally recognized emotion. But there are some other things that the Himba do that are very different to us. So you may have come across examples like this of a famous visual illusion. So if you look at these 2 orange circles, which looks larger, the one on the left or the one on the right? The one on the right, and that's a very, very common experience for people. Of course, you'll know there's a trick here. What's happening is, in fact, the 2 orange circles are the same size, and what our eyes can't do is ignore the fact that circles around the circle on the left are large, and they make it look relatively smaller. On the right, the circles are small, and they make the orange circle look relatively larger. So your perception is something that is kind of being affected by the context in which you see things. I would have said that's a universal aspect of how human brains see things, and it's not. If you give the Himba this visual illusion, they are not tricked by it. They see the same circles. If you do a different... Sorry, would you mind going back, Natanya? That was my fault. If you look here, this is a sort of experiment psychologists really like doing. Look at that, sir. Your task here would be to press a button saying left or right, depending on which way an arrow is pointing. Is it left or is it right? And you press the button. Psychologists love this kind of thing. And what happens with humans is that if you surround that arrow, the one you're paying attention to, with lots of other arrows pointing up and down and left and right, people can't ignore them. If you are trying to press the button saying, oh, that's pointing left, and in fact everything else is pointing right, you will be slower than if all the buttons are pointing left. Again, I would have said this is an absolutely categorical feature of how humans pay attention to the world, and it's not, because the Himba don't show it. They are much, much better at ignoring distracting information than we are. Interestingly, this only is the case while they live in traditional Himba communities, small communities. If they move to the capital city in Namibia, they start to look like Westerners. So there's something about living in urban environments that seems to be doing this to our brains. So we can also look at different sorts of brains if we look at different sorts of animals. Hardly bear the excitement of, oh, there we go. Platypus. Who doesn't love a platypus? Well, actually, I've gone off them a bit. They turn out to be, along with some shrews, one of the very, very rare toxic mammals. Venomous, in fact. The males have got venomous spurs on their hind limbs. Don't let one scratch you. It will get very ill indeed. But they also are more famous for having these fabulous bills. And these bills are highly sensitive. They're sensitive to touch, but they're also sensitive to electrical discharges, something we can't perceive. And the platypus, who actually does not have good vision, will stick their bill into the muddy bottoms of rivers and ponds, and they will pick up electrical discharges associated with worms like there, or insects, or other things it's wants to eat. So their world, the way they see the world, is through this bill, and that's reflected in their brain. If we look at the structure of the platypus brain, almost all of it is devoted to processing information that's coming in from the bill. There's a little bit, the little bits of the green at the back here, that's visual, and then everything going up around here in blue and yellow, and purple is all bill. For the platypus, the whole world is what they're perceiving in that dimension. If we look at another animal, doesn't always get the best press, the naked mole rat. Very interesting. They live underground. They are highly social. They don't get cancer. There's a lot more to know about the naked mole rat. One of the things, I don't think there's enough press about this, is they can move their teeth. Apologise for the absolute horror of this picture, but here's some teeth in action. Anybody remember Conrad Poos and the dancing teeth? Yes, that's strong Conrad Poos energy here. But that's what's going on. And that's because they're in the dark and they're manipulating things and finding out about the world by moving their teeth. If we look at their brains, what you find is, lo and behold, so all those areas in green, that's all devoted to the teeth. In brown, that's the mouth. And then there's the whole rest of the body up at the top there. So the world of the naked mole rat is incredibly driven by what it's feeling with its teeth as it moves its teeth and what's getting into its mouth. It's a mouthful world from a brain's eye perspective. So I'd like to just finish with a couple of points. What's good for your brain? People are always telling you what's bad for your brain, and people will try and often for money, try and give you information about what's going to be good for your brain, but actually some pretty basic stuff is good for your brain. Number one, get your hearing tested. The single biggest preventable cause of dementia across all possible cases is uncorrected hearing loss in adulthood. So if you suspect that you need your hearing tested, and for everybody over the age of 40, everybody experiences about 10 decibel loss per decade. So all of us are on that trajectory. Your ears have got moving parts and they wear out. If you think you'll need your hearing tested, or even if you don't, get it tested. And if you need a hearing aid, use it. And they're not like putting on glasses when suddenly the whole world looks clear. They are hard to get to learn to use. They don't feel right. They feel uncomfortable. Things sound different. Bear with it, because it will be reducing your likelihood of getting dementia by tenfold. It's incredible. It's absolutely extraordinary. So the mechanism for this seems to be, because it's across all kinds of dementias, actually, because if you need hearing aids and you're not using hearing aids, you've got a hearing problem. It is very hard for you to go out in the world and engage with people and take part in activities. And so the problem with hearing is not that it's a risk in and of itself. It's that we use our hearing a lot to communicate with other people, and that's what's really good for us. Again, one of the single most dangerous things you can do to a human is to make them lonely. You need social contact. Your physical health, your mental health, and even the length of your life can be predicted by the size and the strength of the social networks that you have. And I don't mean on Twitter, I mean in the real world, in this room here. And the mechanism for this seems to be, those are the people that you talk to. You sit down and you talk to them, and you laugh with them. And that seems to be what, not only friends are good because they will do things for you, they will help you out when you're in trouble. Friends are good for you because you relax when you're with them, and you laugh when you're with them, and you talk with them, and you are in a better place in a well-being sense than you had been on your own. So that's the mechanism there, is it's loneliness that's the real danger. And the other thing, I had a colleague the other day say, oh my God, we've spent billions and billions of pounds on research into Alzheimer's. Sorry, would you mind going back one? I skipped one. Back again, sorry. Thank you. All we've found out is that activity is really good for your brain as well. Now, you're allowed to start throwing shoes at me at this point because you're completely fed up of people telling you activity is good. It doesn't have to. I'm not saying go and run a marathon. I'm just saying move about a bit. This is probably for two reasons. Number one, your brain is exquisitely dependent on the health of your cardiovascular system. Your brain is about 1 to 2% of your whole body weight, but it uses at least 20% of the circulating oxygen at any one point in time. It is a very, very metabolically hungry organ, and you need to feed it oxygen. So anything that's going wrong with your heart or your blood vessels will start to have big effects on your brain before any other part of the body. So this converse of this is, the more healthy you are, the better your brain will be. The second point, do you remember I said right at the top, you've got 86 billion brain cells and you're born with almost all of them? Well, there does seem to be one exception. In rats, okay, so big proviso, in rats, it has been shown that given the rats opportunities to exercise, to run, is associated with the growth of new brain cells in the hippocampus. Part of the brain, very important for memory, very important for spatial navigation, and which is critically impacted in diseases like Alzheimer's. So it may be that will turn out to only be in rats, but you might find out that it's helping you anyway to get a bit more exercise. The scale of all this is dizzying. So this is a little chap, a little worm, a little nematode worm, and he has the distinction of being the first animal whose entire neuronal system was mapped out in 2012. And he's got 302 brain cells in his whole body, organized in this way. Now, he can do a lot with that, or she. They can learn cues to the environment about where food is. They can learn to avoid aversive environments. If you train one of these nematode worms to find food by following light, and then you clone a new nematode worm from one cell of that original nematode worm, that new clone also knows how to find food by following light. Got to tell you, that does not work for humans, okay? But it's a lot. They're doing a lot with 302 brain cells, nerve cells. You've got 86 billion brain cells. There is no known limit to human memory. There's no known limit to the amount of languages a human can learn to speak. The limit is time. So the power of everything that's happening that humans can do is resting on the size and the flexibility of the network that you have. And just for the scale of it, just to use John Allen Paulos' way of thinking about how very much bigger your brains are. If we think about the nematode worm, if we think of neurons as seconds, forward again. The nematode worm has got 302 neurons. Oh, sorry, would you mind going back? And that's about 5 minutes. We've got 86 billion neurons. That's 2,727 years. It's absolutely dizzying how big and how very powerful your brains are. And I would just like to say thank you very much for your time. And next slide, please. I have got a book. Thank you. Thank you, Netanya. Thank you. Sorry.
Thank you. Sophie Scott, eh? Fantastic. And all of that was produced by wonderful technologies, which we didn't have very long ago, did we? We didn't have fMRI and...
It's like the first days... Sorry. if you think about everything that Lawrence was talking about, what we know about the heavens, and we've literally in the last 25 years got these tools to start looking at the human brain. So we're in the absolute early days of this journey. Thank you.
Thank you. And this is going to pose problems for humanity because we have to work out how to relate to all these changing technologies. And we've got just the man to help us do that. Can we have Blay Whitby, Professor of Ethics?